So we've spent some time now talking about the linear algebra structure of the solutions that we're looking for to nth order linear differential equations. A bunch of theory, basically. And there are some powerful tools that we have in play there. So what we'd like to do now is start to actually get our hands dirty and let's start actually solving some specific linear differential equations. We're going to focus our attention here at first on homogeneous constant coefficient linear differential equations. Okay. All right. Now, before we get going, let's focus on this word constant coefficient. It means exactly what one would think, namely that the coefficient functions are constant. And at a glance, it would appear that considering such differential equations is maybe a little too trivial. I mean, what are the odds? I mean, the world's full of things that are changing, and what's static anyway? So why are constant coefficient linear differential equations interesting? Well, as I note here, even though lots of things are moving and changing in the world, very often the coefficients in the differential equation you would write down to understand a moving and changing system, very often those coefficients are actually constants. So here's some nice and easy examples. Suppose you're considering what we call forced harmonic motion. So we have a mass, and it's on the end of a spring. I'll just represent like that. On the end of a spring, and it's attached to something firm, ceiling joist, what have you, there. And suppose you take this mass and you pull it down, and then you let it go. Well, it's in some way or another, it's going to bounce around, right? And maybe in addition to just letting it bounce, maybe there's some sort of external forces involved. Maybe there's a changing magnetic field that's pushing the mass up and pulling it down as some function of time. So a lot of things going on, but if you write down the entire differential equation, we'll worry about all the details a little bit later. Here's a differential equation that describes that system, where y describes the position of the object we're interested in. And notice that what we have is a second order differential equation. Notice furthermore that it's linear, right, in terms of the structure of how this is written down. And looking at these coefficients, the coefficients are mass, which is constant, the friction coefficient, which under various circumstances, very common circumstances, is constant, and the spring constant, which, well, of course, per the name, is constant, again, under certain conditions. So this is a complicated system. There's a lot of stuff that's going on, and things are moving around, and forces are changing, and the position is moving, and it's accelerating and decelerating. Lots of stuff is happening, and yet it is truly a constant coefficient linear differential equation. Okay. Likewise, here's another scenario. LRC circuits. The students who have had a circuits course in engineering have already seen equations like this. And here's a differential equation. We won't go through and talk about the physics of where this equation comes from, but you'll see that we have a linear differential equation for I, that being current, and various derivatives. Right, so this is a linear differential equation, and these coefficients are the inductance, resistance, and capacitance of the other items in that circuit. And very often, these are constants. So these are just two of many examples. There are plenty of examples of non-trivial, natural physical situations where we actually have constant coefficient linear differential equations. We're going to start off by considering the homogeneous case. We'll come to the non-homogeneous case a little bit later. All right, now how are we going to find these solutions? Let me first observe we have solved some of these kinds of differential equations previously. Here was an example. It's kind of a cheap solution in this case. There it is. Note constant coefficient. These coefficients, and then there's a missing, there's a 0 y prime term that I didn't write down, but all of those coefficients are constants. Okay. Now, how did we solve this one? Well, like I say, cheap solution. We kind of played guess and check, right? We got lucky here that we happened to be able to find, by clever observation you might say, a couple of solutions. Now, there was more than that. We took these two solutions and we used some sophisticated ideas of linear algebra to turn two solutions into infinitely many solutions, and then furthermore, with some more sophisticated ideas of vector spaces and dimensions and bases, argued that not only can we turn those two into infinitely many solutions, but that this is all of the solutions. Right? So there were some heavy ideas that followed, but our initial foot in the door was we got lucky. All right, so is there a more sophisticated means of finding these foot in the door solutions to get us started, onto which we can start applying ideas of linear algebra? And not really. It's the bad news. The good news, though, is that we're going to continue to guess and we are going to continue to get lucky. That's the wonderful thing about it. So here's our constant coefficient homogeneous differential equation. And here's my guess. Let's suppose we guess this. E to the power of, well, some constant times x. We'll worry about what that constant is in a minute. Did I guess right? Is this a solution? Well, we take this, we plug it in, see what the differential equation turns into, and it turns into this. Now, I'll leave this as an exercise for the students to work this out, but if you take the nth derivative of that function, every time you take a derivative, that sort of kicks out a factor of lambda every time you take a derivative. And so these n derivatives here, the n derivative turned into n factors of lambda, and the n minus 1 derivative turned into n minus 1 factors of lambda, etc. And a little bit of algebra, not hard to persuade yourself, but the differential equation turns into this. Okay, now students should make sure that you can fill in the blanks on that algebra. Okay. So, did we get a solution? Did this work? Well, at a glance, doesn't appear so. But here's the thing. If this should equal to 0, then we did get a solution. We guessed right if that's equal to 0. So we become very interested in the situation of finding a number lambda that makes this polynomial equal to 0. Said differently, we become very interested in finding roots of polynomials. And furthermore, we become very interested in this polynomial in particular, and this polynomial is called the characteristic polynomial. This is the polynomial that we need to solve, whose roots we need to find in order to solve this differential equation that we're actually interested in. Every time you find a root of this polynomial, then that means that you have correspondingly found a solution to the differential equation.